Aloha, Richard Halverson here. In this video, I'm going to take you through the first four sections of chapter 21 on graphs. So let me share my screen. All right, here we are, and let's get started. Most everybody is familiar with graphs. You use them all the time. This is an example. These are some examples of graphs. We have a subway map. This is a map of the energy grid, and this is an electronic circuit. And so these are examples of graphs of how graphs are used. A little vocabulary. Nodes are called vertexes or vertices. A vertex is a node, and an edge is the line between the vertexes or between the vertices. And so here we have an example of a graph where we've got the vertexes would be these components to a computer system, computer network in an office maybe, and the lines the edges would represent the connections between them. Here in this example, the lines would maybe represent friendships or people who know people. And so this section here, or these questions, make sure you understand what vertices are and what edges are and so on, and the meaning that's they're trying to convey with the graph. There's a couple other terms. Adjacency means two vertices are connected by an edge, and that means they're adjacent to each other. A path is a sequence of edges to get from one vertex to another vertex, or a starting vertex and an ending vertex. The path length is the number of edges in the path, is the number of edges in the path, and the distance between two vertices is the number of edges on the shortest path between the two vertices. So this talks about being adjacent, and we can see that server 1 and server 3 are adjacent, but server 2 and server 4 are not adjacent. So these are edges here which connect these components, and the shortest path between PC 1 and PC 2 is from E2 to E5, not E1 to E4 to E6, so on. Adjacent paths and so on. So make sure you understand this. Some more applications of graphs. Here we use graphs to used in navigation, and the edges refer to the time that it takes, and the vertices would be stops. Looks like intersections. So that's one. Just make sure you understand that. Flight navigation, the vertices can represent airports, and the edge weights can represent flight durations. So here's another example where product recommendations, where in this example we have a particular a customer is coming in and purchases a particular product, and then these the adjacent nodes represent products that you could suggest to the buyer. So someone comes in looking for a game console, you can recommend these kinds of things. If someone comes in and purchases a blender, you might suggest dishwashing soap or something. It turns out in this example, for some reason, somebody who's buying, they must have found that somebody who purchases a Blu-ray player often, purchases a blender. That's weird. Somewhere it says that here. Maybe connections might also represent common purchases that occur by chance. Maybe several customers who purchase a Blu-ray player may also purchase a blender, whatever. Another use of graphs, another application is professional networks or friendship networks, people who know people. And so this section just gives you examples. You can think of lots of them. All right, there's two ways that we represent graphs. One is using adjacency lists, and the other one is an adjacency matrix. Adjacency matrix. First of all, adjacency lists. So you list all the vertices, and you list all, and then you have a list of adjacent vertices for each vertex. So so vertex A, for example, vertex A is adjacent to B and C, so that's why B and C are listed here. B is adjacent to A, C, and D, so that's why these are listed here, A, C, and D, and so on. Advantages of adjacency lists is it only requires O of V plus E number of nodes of space. It's actually two times V, I think, because each vertex, each vertex is in here twice. A is, because each vertex that's adjacent to a vertex, each vertex that's adjacent to another vertex is in here twice. Here A is adjacent to B, and then here we have B is adjacent to A. The disadvantage of adjacency lists is that it takes O of V in the worst case to determine whether or not two nodes are adjacent, two vertexes are adjacent. And we'll see that in when we use adjacency, when we use an adjacency matrix, it's only O of one. So anyway, so this is good for sparse. A sparse graph has far fewer edges than the maximum possible. So for a sparse graph, adjacency lists are good. They're not as wasteful. And so so this makes sure you understand adjacency list. Here's bus routes. The following adjacency list represents bus routes. So when they ask how many buses in this example here, for example, how many buses are needed to go from Livermore to Hillsborough? Well, we see that just one. Livermore and Hillsborough, there's a bus route right between them. They're adjacent. So that means that the answer is 1. I think the answer is 1. Yes, it is 1. What's the minimum number of buses needed to go from Belmont to Hillsborough? Okay, so Belmont and Hillsborough, Belmont is not adjacent to Hillsborough. Okay, Belmont's not adjacent to Hillsborough. So we have to find, we can start if it's 2 buses, then we need to find a city that is adjacent to both Belmont and to Hillsborough. And look, Belmont, okay, Marion City is adjacent to both Belmont and Hillsborough. So what you can do is you can start at 1 and you can go to Marion City and then you can go to the other. Sonoma looks like the same too. So what is this? Minimum number of buses needed to go from Belmont to Hillsborough. You can't go directly, but if you 2 buses, you can do it. And so the answer would be 2. The following path from Livermore to Marion. It's asking if this is a path from Livermore to Marion City. Well, is Livermore connected to Hillsborough? It is. Is Hillsborough connected to Sonoma? Hillsbury, Sonoma, it is. And is Sonoma connected to Marion City? Sonoma, Marion City, it is. So it is, this is a path from Livermore to Marion City. And it is. Okay. All right, a challenge activity. Let's do this. Select this. Let's do here. Let's okay. In this first one, here we're creating this adjacency list representation here. And so basically vertex A is connected to what, and then C, and then D. Vertex A is connected to C, D, and B. So this should be a B right here. So you'd pick B, because one is a B. For this one, 2 should be the vertices that are connected to B. And so we've got A and D here with B. We've got A and D, and the one that's missing is C. So this should be a C. So you pick C here. Okay, so you can do that. I'm going to do the next one. Okay, I'm going to do this one here. This is a harder one. The following adjacency list represents bus routes. Okay, here we are in the same cities. What is the minimum number of buses needed to go from Livermore to Marion City? Well, does it go directly? Livermore does not go directly to Marion City. Okay, so let's find a city that goes to both Livermore and Marion City. Livermore, Marion City, Livermore, Marion City. Okay, looks like Sonoma is connected both to Marion City and to Livermore. So I'm going to say 2. That's what I'm going to say. Yeah, very good. Okay, so that's that one. Now let's look at adjacency matrices, and this will be the last section in this video. After this, it's Java. All Java. And then your assignment is on this one here. Programming assignment. All right, so anyway, adjacency matrices, or matrices, however you want to pronounce it. So the way this works is you have a matrix here, and you got all of the vertices. You have a row for every vertex. You have a column for every vertex, and you put a 1 in the intersection. So if they're adjacent, if they're not adjacent, you don't put a 1. You put a 0 or put a nothing. So here we have A is adjacent to B and C, but not D. So A is adjacent to B and C, but not D. And A is adjacent to B and C, but not D. So that's how this works. You notice everything is in here twice again. And you notice if you draw a line right down here, draw a line right down there, these two sides mirror each other. The AB and the AB, and the C, AC and the AC, and so on. So click through this to make sure you understand it. Make sure you read this. Okay, here we're gonna fill in. Okay, so what's A? Okay, W is connected to every. It's connected to every other one. So this must be a 1, and this must be a 1. So A must be a 1, and B must be a 1. Okay, you can finish them. Okay, the following adjacency matrix represents a map of the city's electrical power grid. Sector A's power grid is connected to sector B's power grid, and so on. So line down the middle here. Okay, how many edges does D have? Well, we have D here, and it's got 1, 2, 3. Oh, we have D here. It's got 1, 2, 3. Okay, so it must be 3. What do you know? How many edges does the graph contain? Well, you can count up the number of ones and divide by 2, or you can just count up the number of ones, draw a line like this right there. Oops, draw a line right there, and count up in the upper, count the number of ones in the upper right half or the lower left half. 1, 2, 3, 4, 5, 6, 7, 8. The answer is 8. Lo and behold. Okay, assume sector C has a power failure. Can power from A be diverted to E? A is connected to, A is not connected to E. A is not connected to E, so the answer is no. Answer is no. Is the following a path from sector A to sector E? So you go from A to D, from D to B, and B to E. A to D, D to B, and B to E. Yeah, I guess that'll work. So the answer should be yes. All right, let's do this one last challenge activity. Okay, in this first one, select the missing elements to complete the adjacency matrix representation of the given graph. Okay, so B is B connected to A? No, it's not. So this would be a 0. For B, is C connected to E? C, E, no, this would be 0. So you put a 0 there. Is C connected to D? Wait a second. Can you just go look at, this should be the same as this. This, oh, it should be the same as this. This should be the same as this. This should be the same as this. And yeah, B should be the same as this. That's 0. C should be 1. Is that right? D and C. D and C. Yes, it is a 1. So that's what that is. And then D and B. Oh, B was a 0, so D must be 0. D is C and E. C and E. Yes, it's 0. So that'd be 0. All right. Let's see what the second one is. The adjacency matrix of a graph is given below. How many edges does C have? Well, you can just count up the number of 1, 2, 3, 4, 5, 6, 7, 8. That's all. That's because they mirror each other, you see. So you put that number in here. How many? Oh, I'm sorry. This is the wrong question. How many edges does C have? Well, C has an edge here and an edge here and an edge here and an edge here. So it looks like C's got 4 edges. Okay, so you put a 4 here. And how many edges does the graph contain? That's the 8. 1, 2, 3, 4, 5, 6, 7, 8. Is that right? Yeah. Yeah. These two are represented here, here. All right, so the answer here is 8. All right. So I've let's see, where's my, oh, there it is. All right, so I've taken you through the first 4 sections of the chapter on graphs, and next time we'll dive into the Java. Thanks for watching.